Hello, everyone. My name is Sashi Obilisetty, and it's my absolute pleasure to welcome you to this tutorial titled Shift Left with Google Cloud. By way of introduction, I have over 2+ decades of experience in chip design software and over 5 years of experience in building AI and ML solutions for EDA. At Google Cloud, as Chief Architect, I'm involved in driving our Silicon Solutions vertical. Prior to Google, I spent about 11 years at Synopsys, where I was Group Director R&D working on several successful technology initiatives. Now that we have that out of the way, let me give you the high-level agenda for today. I have two other co-presenters with whom I will be speaking today, Peeyush Tungnawat, Principal Architect at Google Cloud, and Rajiv Malhotra, Director of IT at AMD. I'll be starting the presentation with an introduction to Google Cloud and silicon design on Google Cloud. Peeyush will be covering a few EDA-specific topics in detail, and he'll also be showing a very interesting and highly applicable demo of how a functional regression can scale by leveraging cloud resources. And finally, Rajiv, who's with AMD, will share details and insights about AMD's cloud journey, specifically from a chip design lens. We live in interesting times. Every industry is going digital at a very aggressive pace. IDC, an industry market intelligence company, predicts that in just about a couple of years, approximately 70% of enterprises will be integrating public clouds in their environments. So that's huge. And soon after that, it is also expected that a significant amount of IT spend, in fact, over 50%, will go towards companies transforming themselves to be more competitive in their market segments. Cloud enables the digital transformation of companies, and several studies indicate that multi-year, long-term cloud strategy is essential for companies. It is impossible to talk about digital transformation without talking about artificial intelligence or AI. In Andrew Ng's words, AI has become the new electricity. And over the past decade, AI is enabling innovations in retail, finance, automotive, and also in semiconductors. Given the exponential growth thus far, it's hardly surprising that this space is expected to continue. And there are indications that by 2025, an astounding 90% of new applications will embed AI. It's probably fair to say that Google needs no introduction. It has become part of our life, and almost everyone in the world who's actively using the internet is likely using one of its many billion user services, such as Gmail and YouTube. Google Cloud came about in 2008 when we announced our App Engine product. Now, about 12 years later, we have over 90 products in Google Cloud, including infrastructure, data management, and AI solutions. In this talk, you'll hear in detail about some of the solutions. In our CEO's words, cloud is a long-term investment for Google, and we are here for the long run. At Google Cloud, we have a dedicated sales, professional services, and partner organization focused on building and enabling the semiconductor vertical market, enabling quick proof of concepts and building strong ISV relations. I'm sure you're asking the question, what can Google Cloud do for me? It turns out a lot. Let's first start by making sure we're on the same page. The silicon design flow is a complex process with numerous steps, and what you see here is a high-level view of the entire process from the time a chip is conceptualized till the time it is realized in silicon. In any silicon design process, there are 3 to 4 milestones, depending on whether you're a fabless company, a foundry, or an IDM. There's the front end, phases between the architecture specification and the netlist generation, and the back end, which takes the netlist and creates the GDS2. Now let's look at the flow from a cloud perspective. What is important to note in this flow is that the needs of infrastructure change as designs move from the front end to the back end. For example, in the front end, the memory requirement for tasks like RTL simulation is quite low. However, front-end verification needs a tremendous amount of compute. In contrast, the back-end processes require machines with much higher RAMs, sometimes over 1 TB. Further, each of these phases generates a lot of data, which can be leveraged a lot more than it is today to make real time decisions, build ML models, and ultimately design chips faster. In the previous slide, we talked about the silicon design flow. Now let's look at how cloud enables silicon design. First, there is the inherent elasticity that comes with cloud. You can get compute and storage when you need it. The 8 to 12-week provisioning cycles are no longer necessary. There are several places in the silicon flow, such as the front-end verification and the back-end physical verification, where access to more compute can accelerate time to market. Second, when it comes to silicon design, it is not just the amount of compute, but the type of compute. Several EDA tools perform better when the memory per core is configured for optimum behavior. Similarly, access to local SSDs can significantly speed up processing. Compute and storage choices on cloud ultimately enable you to get better QOR. The silicon chip design and manufacturing process is very extensive, and in many cases can be classified as a big data problem. It has the three V's, the volume, the velocity, and the variety, but typical end user flows lack the infrastructure needed to enable data-driven insights at scale. Advanced analytics for data and metrics from an active flow has shown to reduce the number of product delays. Importantly, a clear data strategy also builds the foundation for AI and ML. In many ways, this is the golden age of semiconductors. We are seeing many more design starts in the past few years than before. This is driven by use cases in AI, low power, automotive, and in many cases, a combination of all three. Semiconductor companies are facing a severe shortage of skilled engineers. And with its seemingly instantaneous access to data centers, cloud makes it easy for companies to open design centers wherever the engineers are. This in turn ensures that companies remain competitive and innovate more. So, what are the technologies available for next generation chip design? Later on in the presentation, you will hear a lot more about them, so I'm not going to spend too much time on this. I do want to point out that in addition to the multiple hardware architectures and storage configurations, Google Cloud has the industry's most secure, high throughput, and low latency network. Cost efficiency, which is a concern for many cloud adopters, is also built in through low-cost preemptible machines and committed use discounts. We also work closely with our partners in the semiconductor ecosystem. Minutes, I will also cover in detail AI and ML products available to Google Cloud customers. Cloud technologies are extremely well suited for verification jobs and for building high-performance verification environments. We will look at three very common flows in verification: the functional simulation flow, the formal verification flow, and the static analysis flow. Depending on the tool you're running, the input to the DUT changes. A typical mature verification flow includes all the use cases described. So the question I'm interested in answering is, how is Google Cloud enabling you to simulate faster, verify better, and analyze with little or no latency? Let's start at the infrastructure layer. All the cases described above perform better with access to more compute, and this is a key way for simulation and formal verification workloads to leverage cloud. Further, it is not just about machines. Google Cloud offers very powerful multi-core machines with many choices. VM to VM communication is very fast in the cloud. Even if you're looking at a hybrid model, a 100G dedicated connect can make the connection appear very fast for debug needs. Once the compute is in place, an efficient and high-performance flow can be built with the many data management products that are offered on Google Cloud. Many of them are offered as managed services, which means that you do not need to worry about the maintenance of these systems. Instead, you can focus on ensuring you're building the dashboards and the advanced analytics you need to build. And finally, the data that you consistently collect can form the foundation for applying AI and ML in your flows. When it comes to AI and ML, Google Cloud has the best-in-class solutions, whether it be hardware or software. But more about this later. And finally, Google Cloud has about 90 plus products, and some of the products relevant to verification are listed here, such as the compute engine, cloud interconnect, GPU, persistent disk, cloud storage, cloud data store, cloud SQL, and PubSub, data flow, BigQuery, and of course, cloud machine learning. I briefly touched upon AI ML products in the previous slides, and I want to go a little bit deeper into it here. AI can be thought of simply as a machine performing human tasks, and ML is described as the ability of machines to learn without being explicitly programmed. Google Cloud offers multiple solutions that enable end users to successfully build AI-enabled applications very quickly. First, we offer pre-trained APIs and AI solutions. These are supervised learning models, but where no training data is needed. For example, the Vision API can be used for image recognition tasks. Then there is the custom AI with AutoML. In this low or no code approach, the end user provides the data and the model is made available. I'll delve into it further in the next slide. And finally, we also have end users who are experts. And for the experts out there, we offer end-to-end AI solutions such as the TensorFlow Enterprise, notebooks, and explainability solutions. The way AutoML works is we provide a graphical, codeless interface guiding users through the end-to-end ML lifecycle with significant automation. We help you easily define your data schema and target, analyze your input features in the feature statistics dashboard, automatically train your model, including automated feature engineering, model selection, hyperparameter tuning. You can also evaluate your model behavior before deploying to production and deploy your model in just one click. Through this, we can help you ensure that what used to take months can now take weeks or sometimes even days. We automatically search through Google's Model Zoo to find the best model for you. It could be a linear or logistic regression for simple or small data sets, or advanced deep ensemble methods for larger ones or neural networks. We are trying to bring the best from Google AI research in our AutoML solution. At Google Cloud, we strongly believe that silicon design can benefit greatly from adopting cloud. And to enable our customers to onboard faster, we have a deep organization that can help you. We have programs such as the EDA Essentials program that you can use to ramp up your environment. We have extensive documentation on reference architectures that you can use in your environment. Our teams are located worldwide. We offer white papers, webinars, and trainings. We believe that any verification environment can be transformed to be faster and more effective by adopting cloud and applying ML methods. We will meet you wherever you are, whether you're looking for a hybrid flow where you just burst to cloud or your verification is all on the cloud. Thank you, and we look forward to being your partner in your cloud journey.
Thank you. Hi, everyone. My name is Peeyush Tungnawat. I am a principal architect at Google Cloud, and I focus on making our semiconductor customers successful with GCP. So today, I'll walk you through the relevant GCP infrastructure components for EDA in a little more detail. Let's jump in. So before we begin, we just wanted to highlight some of the GCP features that highlight flexibility and ease of use. So let's look at the core components for EDA, right? From an EDA perspective, you need the latest compute. GCP has been the first with many industry-leading offerings, including Skylake VMs, NVIDIA GPUs, V100s, and Google Cloud TPUs. We also make it very easy to upgrade to the latest hardware. So you can, again, specify a flag and get the latest generation CPU platform. In addition to this, from a storage perspective, we also offer multiple performance-oriented options for storage. ranging from GCP native to the ones offered by our technology partners. In terms of security, you get the Google grade security with GCP, which means that your data and IP is much more secure. And then the global network, we'll talk more about this in the later slides. Let's look at the additional value that you get. So eventually, the overall thing is, it's a lower cost. So again, a combination of custom machine types, per second billing, and so you pay exactly for what you use. You also can start thousands of VMs in seconds, which means that you can start and scale your simulations faster and pay for only the time that you run it. And then in terms of partnerships, we have really great partnerships in place, ranging from EDA tool providers to storage partners to schedulers and many more in terms of EDA and HPC domain. And the last thing, but not the least, is the AI, ML, and big data. And as you know, Google has been a leader in this space and has been working on sharing the technology with broader community through GCP. Next, let's look at the security aspects. So as you know, security is very important because of business critical information, intellectual property, both yours and third party. And again, the traditional approach has been to just keep it all on-prem behind your firewall. And knowing what we know about network attacks and other things, your IP and data is much more secure on GCP, and we'll tell you why that is. So let's look at the GCP security approach. Security is basically built ground up. And the core philosophy of building security through progressive layers and at Google scale is what we call defense in depth and at scale by default. So if we see the bottom layer, our hardware is purpose-built, controlled, and hardened by Google. We also don't have any implicit trust even within our own services. So all identities are strongly authenticated. We have multiple layers of protection against network attacks, denial of service, and things like that. Your data is encrypted at rest and also in transit. We also provide additional tools for operational continuity and monitoring, things like cloud audit logging. And lastly, we also offer confidential VMs, which is a new offering that allows you to encrypt data while it's being processed. And then, if we take an example of Meltdown and Spectre, if you remember those microprocessor issues in 2017, the way Google Cloud is architected really allowed us to use a VM live migration technology to perform updates, and there was no user impact, no forced maintenance windows, and no required restarts for our Google Cloud customers. So that's security. Next, from an EDA perspective, the heart of it is compute and storage. And so let's talk about those things. So again, the story with GCP is imagine a regression that used to take days and completing that in few hours by scaling significantly on GCP. So we offer high performance compute, but with equally high flexibility, which means that we have both predefined and custom machine types. It works with your favorite scheduler, and you have an option to put all your VMs on the same host with the offering called Sole Tenant. Okay, custom machine types allow you to right size your VMs. And what it means is that we offer this ultimate flexibility with custom machine types. So for your EDA jobs, you can pick precisely the amount of memory and CPU that your jobs need. It's literally a slider, just like we show here. We'll also show it in the demo. And so you don't over provision, you don't pay for anything more than what you need. It's a standard feature, and so there is no additional cost for that. Okay, as you can see, we offer many VM types. C2 family is really a great fit for EDA and HPC workloads. We also have a great balance of price performance with AMD EPYC Rome-based VMs called N2Ds. We also offer memory optimized VMs, and again, these are machines with high memory capacity, and they go all the way up to 12 terabytes as of now. So as I said, C2 family is really focused on EDA and HPC workloads. Very impressive performance. They offer the highest performance per core on compute engine, and has Intel scalable processors, Cascade Lake, and up to 3.8 gigahertz sustained all-core turbo. As you can see here, it has 40% higher performance per core when you compare it with the previous generation N1 machines. So that's compute optimized. Let's quickly talk about a very interesting feature of Google Cloud called preemptible VMs. And what it is it's really a way or mechanism for Google to offer any excess capacity to customers for up to 80% discount. So again, exact same VMs, exact same startup mechanism. You just add a preemptible flag in the start command, and you get the machine for up to 80% discount. Great for batch and high throughput jobs. Again, obviously there are some conditions, so maximum runtime is 24 hours, and it can be taken back or preempted with a 30-second notice. So that's security and compute. Next, let's talk about storage. So when you look at it from an EDA workload perspective, your NFS can be hosted with shared file storage on Google Cloud. On the right side that you see the green boxes, you can choose the same providers that you have on-prem, NetApp, Isilon, or you can choose more cloud native offerings like Google File Store. So really we offer flexibility to customers in terms of what they want to do. From a block storage perspective, the data you have on-prem on a hard drive can go on the same offering on GCP if you want that. If you want fast local storage, there is an option of local SSD. But again, all of these things in cloud also offer a mechanism to be more optimized, which means pay for performance only when you need it. And that brings us to a very special offering, which is called object storage or Google Cloud Object Storage. So again, as I said, this is the area where cloud in general provides a great price performance opportunity for EDA. Very cost effective, no pre-provisioning required. So you can store and keep adding data and scale to any amount of data that you have. From a design pattern perspective, here is one thing that you can consider. So, object or blob storage becomes your primary upload and download store. And then you can quickly copy data from GCS to your storage and instances prior to launching a job. Obviously, it needs to be customized for your requirements and setup. and there is some work involved. But once that is done, it becomes a really cheap storage pool that is highly reliable, secure, and you're only paying for performance when you need it. So again, you can be very smart with this and create an architecture that allows you to take advantage of this offering. Okay, so next is file storage. As you all know, file storage or NFS is a really critical part of any EDA workload. And we offer a native option, as I mentioned earlier, called File Store. We also offer integrated partner technologies to choose from, like Dell Isilon, PowerScale, NetApp, CVS, and CVO, and DDN Lustre. So you can choose the right offering based on your workloads, required performance, or preference, and pick the one that really works for you. Okay, so that brings us to network, right? And why is this important? So again, this is a great example of Google scale, first of all. So as you can see, this is our global network. The great thing about this is Google owns many of these submarine cables that we are showing on this diagram, including Trans-Pacific, Transatlantic, and it improves security and make the traffic really fast. So as an EDA customer, why would you care about this? Consider a scenario where you have multiple design teams working in different regions in the world. In an on-prem world, they either connect to a few central locations, and some team has to suffer with the latency, or they have their own locally installed infrastructure. In that case, they really are stuck with that infrastructure, and they pay for it irrespective. So with GCP, you have an option to reduce the overall infrastructure required by either selecting fewer locations without delays because of this global network, or scaling each region when really needed and shutting down the whole thing, whole setup when you're done. So again, depending on the phase of your design life cycle, you can make those decisions across the world, and this global network gives you the flexibility to do that. Okay, this is basically a typical flow for our reference architecture, which we will discuss. Let's go to the reference architecture. Again, this is our generic reference architecture for EDA workflows. We understand that every customer will have a different setup, and we usually work with our customers to propose the right one based on the requirements and preferences and priorities. So on the left, you will see a typical on-prem setup, license servers, LSF host, or Slurm, worker nodes pointing to NFS, and again, oversimplified on the left. On the cloud, you can also have the same setup, similar setup, like from a scheduler perspective. You can have a Slurm, which is more cloud friendly. You can also set up LSF. It could be a standalone or through a connector. And then from a license server perspective, you can choose to keep it in the cloud or keep it on-prem. It really doesn't matter. It really depends on the amount of workloads that you have. Scaling is handled by managed instance groups that contain the worker nodes. So it can scale up or down depending on the jobs. And then the VMs basically refer to the NFS storage for your tools and libraries. Any data that you upload from your on-prem and the output of those jobs could be returned to object storage, the thing that I talked about. And then eventually it flows through a data pipeline, which means that it's processed and stored in a data warehouse called BigQuery which has very cool ML capabilities, and it can feed a lot of your data insights and visualizations. So again, there is a lot here, but I think the key things to highlight are the Google Cloud Interconnect, which basically is a 10 gig link between your data center and cloud. And so once you have that established, you see cloud as an extension of your data center.
All right, so let me give you a really quick tour of GCP from an EDA perspective. So we'll do three things. One is we'll create a virtual machine, we'll create an NFS storage, and we'll look at the networking options. So let's get to it. So once you go to Compute Engine, VM instances, you'll see this screen. And here you click on Create Instance. Let's say it's EDA 2. Let's pick the machine family. So you have many options as we discussed. Let's pick the AMD-based machines called N2Ds. And these are the options. So you have standard, high memory, high CPU. Let's say we want to create a machine with a very specific shape. I want 16 vCPUs and 100 GB RAM. Let's select the boot disk. So you can bring your own custom image, or you can pick from a public image. So let's select CentOS 7. Looks good. 20 GB is fine. Select that. And then there are many more options here. The key thing I wanted to show you is the preemptible machine. So if you put this on, then you get a preemptible machine. You can also put the startup script here that will get executed with the boot up time. So that's it. You go ahead and get say create, and you will get a new virtual machine on Google Cloud. Next thing, while it's creating this virtual machine, let's go take a look at storage. So scroll down under storage, you will find file storage. Let's go to instances. This will create an NFS instance for you. Let's go ahead and create one. Let's call this tools 4. You have an option to pick basic or high scale. You can see the difference here. Let's pick SSD for now and go with the default options. Pick the region and zone. And you give the name tools 4. Okay, that's it. And then you go ahead and create it. So let's see if our VM instance is up. Yep. We have our VM up and running. You can SSH into it. And then hopefully by this time, we'll also have our NFS instance. Still working on it. But you see the IP address, and you can see the details of the instance once it's created. Let's look at one of the other ones that I created earlier. So if you click on one of them, we'll have the IP address, location, the performance details, and the networking. And if you have any labels, you'll see them here as well. Okay, now let's jump into the demo.
So let's talk about the AMD cloud journey. So the first question is, why did AMD decide to take a journey to the public cloud? We had some business goals, and the first challenge, the fundamental challenge that we face, and what we wanted to accomplish from a public cloud, is to have a variable storage and compute strategy. As most of you are well aware, demand is pretty variable. We usually plan for a fixed amount of demand on-prem, but because our capacity is pretty fixed, we have to somehow manage the supply and the demand. So the challenges that we face is that the on-prem capacity is fixed with very high utilization, and the short-term demand, it can surge pretty quickly. And when it does happen, it must be addressed. It must be addressed because there are R&D deliverables that are tied to it. And typically the way we do it on-prem, if there's no other resource available quickly, is to prioritize between projects. And that will inevitably impact other projects. Any kind of prioritization, does impact other projects. So our strategy moving forward, why we were looking for a cloud provider, was to partner with the public cloud provider and then focus on the engineering flows that can rapidly be re-architected to run in a hybrid cloud environment. And the idea, the benefit over here is that that there's a couple of benefits over here. One of them is that if we have some ready flows that can easily run on the cloud, then what that means is that we can quickly offload some of the on-prem capacity to the cloud, and then make room on-prem for running some of the other workloads that may need extra capacity. So let's look at some of the opportunities that we felt we had with GCP Cloud. So on AMD on-prem, we have a lot of experience running on AMD CPU instances and optimizing these instances for running EDA workflows. What we found in GCP was a partner that had also offered AMD CPU instances, and we were able to partner with them to optimize them for AMD workflows. GCP also had a large variety of CPU instances and use models. So we were able to pick the CPU instance that worked best for the workload, and then in terms of the use model, we were able to use for on-demand computing an on-demand model or a committed use discount for if there was a certain amount of level of sustained load that was going to be running, then it was advantageous to commit to it, and you get a committed use discount on those instances. And then there's spot pricing, where you can opportunistically run workloads that are preemptible as and when the capacity becomes available. In addition, we felt there was an opportunity with GCP to get very quick access to the latest technology with pretty much no capital investment on our part. So if the capacity was available, we were able to, just use it pretty much immediately. So if we look at the next slide, there were some other added value opportunities, and one of them was the provisioning. The provisioning is very rapid. You just go to a portal and you provision the resources that you want very quickly. The GCP also offers several metrics. A lot of them align with profiling your job and your runtime metrics. These metrics then give you an in-depth understanding of what kind of workloads you're running, and And it leads to what we could think about as spend visibility. Where exactly are you spending your dollars in terms of running these jobs, which will then lead you to be more efficient in your workflow because it gives you that insight. So some of the factors over there are, for example, if is your job really using all the memory that it was requested, and if not, is there an opportunity there to run the job more efficiently? However, before we can get to that point, there needs to be a base IT infrastructure that is put in place, which is a significant amount of work that is done by the IT team. Before we select a cloud provider and a location, we want to make sure that the type of instance we're looking for is available, and it's available at the right level of capacity to match the workloads that we intend to run over there. Also, the IT team needs to do the foundational work to put a base layer for identity management, which is the idea that if whatever your login ID is on-prem, it will also work. Your credentials will then work on the cloud. And then IP security, which is also very fundamental. Because one of the things that the teams will ask for is my IP secure? And there needs to be enough structure in place for you to be able to say confidently that it is secure, or it is as secure as it is on-prem. Also, we want to look at the location of where the cloud is to be able to minimize any latency between the on-prem and the cloud location, and then there is plan for enough bandwidth to run the workloads, because the workloads definitely usually like to see the minimum amount of latency and maximum possible bandwidth when needed. We want to put in the IT infrastructure that helps with migrating the workload. So the first step we look at is to provide as consistent an interface as possible. And so we use LSF as a job scheduler for submitting jobs, but we use Slurm on GCP. So we worked with IBM to develop a connector that IBM provides that will allow LSF to spin up VMs in GCP through using Slurm, and Slurm can be used then to manage those VMs. The benefit here is that the users don't see a difference in their interface and the commands that they're very comfortable using. So they can submit their jobs via LSF, and the jobs will run on GCP. They just have to use a different LSF queue. The second most important thing that we have to look for is also the storage and the performance of the storage. We use NFS for EDA workloads on-prem, and Google has the leading NFS storage providers also. You may find a solution that is virtualized, so that is, or you may find the actual original equipment from the manufacturer available to you through the GCP, on GCP. They will obviously have different pricing and performance characteristics, and you can match them to what you are really looking for. Another key feature we look for is file caching. Because in a hybrid environment, there is a significant number of cases where we will run the jobs with the data is on-prem. So file caching becomes important for those workloads, provided they can take advantage of file caching. The third thing we look for is the ability for the on-prem users to view and post-process the results. Part of the reason we also want to do this is because we want to minimize the egress cost and also the time it takes to download data from the public cloud to on-prem. So having put in place the foundational strategies and understood the objectives and so of why we want to do this, the strategies to run any DV workloads on GCP is relatively falls into place and is pretty straightforward. And we've discussed some of these points in the previous slide. So we are looking for CPU instances that are optimized for DV workloads. So typically, if you look at DV workloads, they are usually single-threaded. And then they may be sensitive to either frequency or cache, and you can find those kinds of instances for the type of workload that you're looking for. There is the capability to take advantage of burst computing to meet your peak demand. In burst computing, the data is on-prem, but you want to minimize your data transfer and egress costs. So what that means is that if you have large data sets, which not all DV workloads do, but the ones that do, you can still leverage those, provided they can be used for multiple runs. So if you're transferring a particular model to run simulation against, if you're going to be running a large number of simulations, then that that just justifies transferring a large data set. Or if you will be running very long runs, so those kinds of data set transfers are not as frequent. So for those kinds of things, burst computing works just fine. There is also the opportunity to do sustained computing. So this is the idea that you take all of the project data and host it in the cloud. That includes any dependencies, it includes any runtime libraries. So all of that have to be carefully cataloged and then put on the cloud. You typically do this for a whole project, so that you can let the project run over there fully independently in the cloud with all the data that it needs over there. And then the results can be viewed or post-processed in GCP, as we talked about earlier. So in terms of future state and added value, we want to re-architect the internal flows to run seamlessly on-prem and on GCP. So the idea here is to make the flows both portable and the job self-contained. So they have all of their dependencies are covered when you submit the job. They have everything they need, including, there are no runtime dependencies on on-prem data. So this will allow us to, easily run the job in the cloud. From the IT infrastructure perspective, we want the on-prem to look as much as possible, as close to the cloud as possible, to have basically the same flows that can run on-prem and run cloud without any changes. And then in terms of added value, this does require a shift in thinking. As an IT team, they're very focused on managing IT infrastructure and optimizing IT infrastructure. So once this would lead to is a shift in focus from moving from infrastructure management to actually workflow management, where you're managing the job, you're optimizing the job, and both in terms of the spend and in terms of performance. There is also the benefit of getting a flexible compute capacity, as we talked about, to align with the project demand cycles. And we create the portable flows that can leverage the resources efficiently. And this is to help optimize utilization of compute resources. And then the fourth we talked about was the analytics to support, to continuously match supply and demand. So if we get enough information about the profile of the jobs that are running, the quantity of jobs, their runtime, their resource demand, we can then meticulously kind of manage both the supply and the demand, and it gives you more flexibility to do that. Okay, thanks very much. That's all I had. So.